is Lorne Nelson, and you can see his title.
I'd like to discuss how we can use population synthesis to understand some of the properties of interacting binaries. And basically, it allows us to investigate the ensemble observables of any subpopulation of interacting binaries. But ultimately, it must correctly predict the observed numbers and distributions of all types of these systems. So self-consistency is very important. Now, I'm going to focus on white dwarf systems, white dwarf compact accretors, I should say, in other words, cataclysmic variables. And you can see an artist's rendition there on this slide. And one of the reasons I'm going to do that is that it's the gold standard for testing the accuracy of population synthesis methods, simply because it involves a lot fewer uncertainties. So how do you form a cataclysmic variable? Well, we start with a primordial binary. The more massive star becomes a giant. It engulfs the secondary star. The secondary spirals in towards the core of the primary. And during this phase, energetics require that the common envelope be blown off into the interstellar medium, and what you're left with is a detached system. So M2 remains pretty much pristine. And then you also have the core of the giant. That's the white dwarf that will accrete the matter. After some time, either on a nuclear time scale for the donor, which is M2, or if angular momentum dissipation mechanisms are effective to shrink the size of the orbit, then the secondary can come into contact with its Roche lobe, and Roche lobe overflow begins. One of the thorny issues related to this particular aspect of the physics concerns the common envelope, and in particular this parameterization that we use, alpha, which is the common envelope efficiency parameter, basically it's a measure of the efficiency for unbinding the envelope of the giant. Now, in what I'm going to show you, we start with roughly 100 million primordial binaries. We choose the primary mass, and for a standard model we use the Miller-Skello IMF. Then we have to choose the secondary mass, where we use some probability law for the mass ratio. Based on the mass ratio, basically the Duquesnoy and Mayer formula that goes like 2 to the 1/4. We choose an orbital period such that it's more or less uniform in log p. And for a standard model, we'll take the birth rate function to do that in a steady state. And then once we have the set of binaries, then we follow the evolution to what we call the post-common envelope binary phase. And in our standard model, we also take alpha equal to 1. So this is a color probability density plot for our zero-age CVs for the standard model. And what you can see there on the right-hand side is a colored bar, which indicates the relative logarithmic probability. And here we're plotting the orbital period versus mass of the donor for stars that are just about to lose mass for the first time, sort of come into contact. Now, I don't really have time to go into some of the details of this, but using semi-analytic methods, it's possible to come up with an equation for the mass transfer rate, which is obviously one of the important observables in these systems, as a function of various terms. For example, it depends on the change in the radius of the donor star on its nuclear time scale, its thermal response to mass loss, the angular momentum dissipation mechanism that's working to basically cause the separation of the binary to decrease. And then this gets divided by the denominator that is largely dependent on Q, the mass ratio of the two objects. And if that denominator approaches 0, then the binary can become dynamically unstable and a merger can result. So when these systems come into contact and mass loss first starts, there are 4 distinct types of evolutions that can occur. The first one, in fact, this plot of the log of the mass transfer rate versus the log of the mass of the donor, and here's the massively accreted white dwarf in the system. For the first case here, the green line, what we see is a dynamical instability. The mass transfer rate simply increases and runs away until it exceeds roughly the Eddington limit of the accreting white dwarf star. And at that point, you would end up with a merger. We also discovered latent dynamical instabilities where initially you have very high rates of mass transfer, but subsequently the mass transfer rate runs away and exceeds the Eddington limit. There's also super soft X-ray sources. Again, the mass transfer rate can get very high, but ultimately it's a stable type of system. Super soft X-ray sources are interesting because the mass transfer rates are so high that you can have steady nuclear burning on the surface of the white dwarf that's accreting this matter. And if you have steady nuclear burning, in other words, no classical novae, the white dwarf can grow in mass, and these could be possible progenitors of type 1a supernovae. And then the fourth case is a standard CV evolution. Now, I'm going to play this little animation here of one of our evolutionary tracks. When CVs evolve, they can evolve to low periods, that's the norm, or they can evolve to higher periods, and that's what we're looking at right here. Here is our secondary that's losing mass to the primary. There's a accretion disk there. At this point, the period is roughly a couple of days. The mass of the donor is about 1 solar mass. This is a chronometer that measures the age in mega years. And our ruler here, our scale, is fixed so that the 0 point corresponds to the center of mass in the system. At this point, the donor is down to about half a solar mass. The orbital period is increasing. In fact, the evolution really speeds up at this point because the donor, although very low mass, 0.3 solar mass, is actually ascending the red giant branch. So it's becoming a giant. It has a helium degenerate core in its center, and eventually all the hydrogen surrounding it becomes depleted, and that envelope has no choice but to collapse. And what you end up with is a double degenerate system. In this case, it's a helium white dwarf of mass about 0.25 and a carbon-oxygen white dwarf of mass 1.0 solar masses. And the orbital period would be about 20 days. Now, the typical CV evolution is as follows. Here we have a 0.6 solar mass star that's losing mass to a 0.6 solar mass white dwarf accretor. And you can see the period starts off more or less at about 5 hours, and it evolves this way. So this is the mass of the donor here, and the log of the period on the other axis. The period decreases until you get to point A, at which point magnetic braking shuts down because the star becomes completely convective. And then the mass transfer rate drops precipitously. And in fact, you don't have a cataclysmic variable anymore because there's simply no more mass transfer as a detached system. At point B, the secondary, the donor, can reattach to its Roche lobe, and the evolution continues with gravitational radiation largely driving the evolution of the system. And the period decreases until you reach a period minimum at about 75 minutes, and then it increases again. So we call these, or this part here, the period bounce. And at that point, when the donor is already sort of a brown dwarf, has brown dwarf type masses, the mass transfer rate also drops enormously. So those are the basic types of evolutions that we're looking at. Now, we cannot compute the evolution of every single one of these systems that is generated in our data set from the population synthesis. This would be about 30,000 different cases. So what we've done is something that hasn't been done before. Namely, we pre-compute a grid of models, and then we archive it, and then using an optimization strategy, we basically interpolate the table of the observables in terms of the initial conditions. So the initial conditions are the mass of the donor originally at the onset of mass transfer, the mass of the white dwarf, and the age of the donor at contact. So in that way, we're able to take into account the possible nuclear evolution of the donor star. This allows us to actually follow the evolution of AM Kanban type stars, which are ultra compacts, to look very carefully at dynamical stability and the formation of long period systems, and to look at the formation of double degenerates. So here we have the results for our standard model for the present day CV population based on the population synthesis. The raw data is on this side. We have the log of the mass transfer rate versus the orbital period. Generally, the orbital period can be measured to within a few percent. The log of the mass transfer rate is not terribly well constrained. But what we see in our results here, again, this is a logarithmic scale, that most CVs actually have orbital periods between 2 hours and the minimum orbital period, probably more than 95%. And that's somewhat unexpected. However, what we really need to do is to scale this data by the mass transfer rate because of observational selection effects. Many of these systems are discovered as a result of their accretion luminosity, and their accretion luminosity goes as the mass transfer rate. So that when we do that, we actually start to see a lot of CVs with periods above 3 hours. So this is one side of the period gap, this is the other side of the period gap. And one of the nice legacies of doing this type of analysis is it allows us to see unusual behaviors, and there's a subclass of cataclysmic variables called SW sextantis stars that show generally very high rates of mass transfer, or at least that's what some people interpret it as. And we may have an explanation for those types of stars, and that's something that we're currently looking into. Okay. So we can fold this information into a period histogram, and what you'll notice when we look at the raw synthetic data or the scaled data is that roughly around the minimum period, so around 75 minutes, there's a bump. There's a higher probability of detection of those types of systems. And in fact, that's what we're now starting to see. And here is an observed period histogram. And we can see some of the distinct features, for example, a period gap between 2 and 3 hours. Here are the long period systems that were successful in predicting. Basically, we cannot form the AM Kanban systems using this particular synthesis. In other words, there should be another evolutionary channel that allows for their formation. But with the SDSS survey, many new low period cataclysmic variables have been detected because it sees so deeply, and it's starting to fill in around the minimum orbital period. It's probably not seeing any of the period bouncers, but with deeper surveys, we should be able to get more accurate statistics. Now, the logical extension of all this is to do a population synthesis for classical novae. For classical novae, matter that is accreted onto the white dwarf basically undergoes a thermonuclear runaway. And many classical novae have orbital periods that are well established. Here's a histogram of the data. That's the gray bars that you see right here. And here's our period gap between 2 and 3 hours. And what you see in this diagram is our numerical simulations, our synthesis for the standard model for hot white dwarf accretors and cool white dwarf accretors. And you can see that for cold white dwarf accretors, the synthesis fits what's observed quite well. So you could then ask yourself, well, are there enough super soft X-ray sources to explain the frequency of type 1a supernovae? And the answer to that question is no. I'll just show you our results here. This is initial white dwarf mass on this axis versus initial donor mass on that axis. These are dot plots. Each dot corresponds to a super soft X-ray system where mass is being transferred at such a high rate that, in fact, the mass of the white dwarf is growing because there are no classical novae. And only the triangles that you see up here, only those cases actually managed to become, or to reach the Chandrasekhar limit. So the mass of the white dwarf was pushed beyond the Chandrasekhar limit. So what we find is that the type 1a frequency is too small by a factor of approximately 20. Now we're fairly confident in that number that there's an order of magnitude discrepancy. Obviously there are a large number of uncertainties, but we've tried to make this scenario work. It's called the single degenerate scenario, where you have a hydrogen-rich donor that is losing mass to a white dwarf accretor, and I just don't see any way that it works. So the conclusions then are that 90 to 95% of cataclysmic variables can be found below the period gap. The relative number of carbon-oxygen white dwarfs to helium white dwarfs is approximately 3. We found it extremely difficult to form ultra-short period systems, the ultra-compacts, the AMCAN bands, because the volume of phase space of the initial conditions is very small, and it simply could not do it, so there should be a different evolutionary pathway. In fact, there are several other pathways by which AMCAN band type stars can be formed. And when you actually combine the spectrum of white dwarf masses and nuclear evolution, and that's something that has never been done before in any population synthesis studies, at least in this accuracy for cataclysmic variables, it tends to smear out the exact location of the minimum period and also the edges of the so-called period gap. Certainly there's an enhanced probability of discovering systems with periods around 8 minutes, but there is no spike, no very sharp spike as some people have claimed. And that was largely because the probability of detection goes like 1 over the time derivative of the period. And so when you get to the minimum period, of course, you would expect a spike if you had only one single evolutionary track that every single system followed. But obviously things are very complex in terms of a spectrum of white dwarf masses for the accretors and also a nuclear evolution of the secondaries. So some of the secondaries can actually have a substantial amount of helium in them when they reach the minimum period. So it also seems that the period distribution of classical novae that we get from synthesis fits the observations quite nicely. And perhaps most importantly, the single degenerate, or at least the super soft X-ray source channel from the progenitors of type 1a supernova just does not seem to work. And so obviously, we would say that there is a different channel for the formation of the progenitors of those systems. Thank you.
Yeah, I have a few questions. So, first of all, which magnetic braking used?
Sorry?
Which magnetic braking used?
Okay. We've used several magnetic braking laws, but the one that was used for the results that I've shown you was the standard Vermont-Swan law.
Do you try to compare the last chance to rates distribution with observations?
Yes, we have. But again, there are quite large uncertainties, so it's a difficult comparison to make.
And
Because of transits and things like that. In other words, the mass transfer rates that I'm showing here, of course, are the long-term secular averages.
the last question is that, so when you decide on the dynamical instability, why make the topic technical?
Well, we actually, I just cut it off at that point for the diagram, but we cut it off because at that point, if we exceed the Eddington limit, then probably, again, we don't understand the physics that well, but probably the accreted matter, of course, gets blown off, and then there's a frictional drag that would lead to a merger of the donor and the white dwarf, and that, of course, we could not possibly get to see the evolution out of that, and that's why it was cut out of this particular analysis.
Yeah, I I know about the cutoff about 10 in minus also a mass spring, but that connects to the white dwarf green state itself as a red giant. Just not sure.
Okay, well, at this point, I think we should let people get lunch. And thank you very much, everybody who spoke in the session.